Right, we're actually starting graphs for constant acceleration motion, and what I wanted to do was sort of get into this topic by looking at the buggy lab and sort of reviewing what we know so far, and then tying this into the new stuff. So, if you remember for the buggy lab, we had these buggies, and they would start at a certain position, and they would just kind of travel at constant velocity like this. And what we'd say is, okay, this is the initial position, and we realized that the slope in algebra equals m. Um, and for us in physics, what we realized is that this corresponds to the constant velocity the buggy's traveling at. And what we realized is that the sloping upwards doesn't mean you're moving faster, it just means that you're moving at a constant velocity like this. So here's one buggy, and it starts at an initial position. And suppose now we have, actually I just move this here. Suppose now that we have a second buggy that starts at the same position. So we'll actually draw this buggy's graph like this. Okay, so it also starts at x naught and it's moving. So we can actually say a couple things here. So the buggy that has the blue line, its velocity also we can label with we'll call it v naught. I'm going to call this v naught of buggy 2 versus v naught of buggy 1. Now what we can say for this buggy is that v naught of 2, the velocity of the buggy, and actually what I should say is the speed of the buggy, is actually less than the velocity of buggy 1. Okay, and the reason we know this is, we can say this because the slope of 1 is steeper than the slope of 2. And remembering, of course, that slope means velocity, we covered that a lot in the last unit. What we can clearly say is that buggy 1 is moving faster than buggy 2. And again, what this means is that if they start off at the same point, if I had like a little ruler and I had buggy 1, we would see it move along, say, from its initial position like this. And if buggy 2 started at the same initial position, what we'd see is if we started at the same time, we'd see buggy 1 just move like this really fast. And what we'd see buggy 2 is it would move a little bit slower, kind of slowly, like that. Okay, so this would get here faster, this would get here slower. That's what this means. The reason I want to actually talk about this is that now that we are talking about objects that are speeding up or slowing down, the graph of the position versus time looks a little bit different. So I'm going to actually erase all this. Now we're going to talk about an object that has velocity that is in fact changing in time. So what we'll do is this. We'll start off, and this actually kind of comes from a Buggy Lab post activity that we did before. If you remember way back, I think it was in learning packet number 2, if you look in the lab section, for the second part, we actually had a graph of motion that looks like this. And almost everybody was able to look at this and say, okay, if this is position versus time, people concluded that this object moves forward and speeds up. And the question is, of course, how can we say that? Well, we're going to look at this from a little bit of a different perspective. The answers that I saw is that people said, well, look, if I go from here to here, and I actually look at the position, what one can say is over this time period here, over this little time period here, what we can say is, in this region, position doesn't change much. That's one way to say it, and that's perfectly correct. And let's compare that. So I've got about 3 blocks of time here. If I look at 3 blocks of time here, and I look at how the position changes, boy, it goes up a lot. Okay, so from here to, so from the second part, let me just do it in blue here. From here to here, we actually see the time change, that over the same time period, this position changes a lot. Okay, so what we say is that in the second situation, the position changes a lot in the same amount of time. So that's one way, and it's one absolutely correct way to say that from here to here we're going faster than from here to here. So I'm going to call this region 2, and we'll call this region 1. And what we can say is we're clearly moving faster in region 2 than we are in region 1. And if we were to actually see a buggy move, we would see it move like slowly, 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 and then quick like that. Okay. Now, another way to see this is that we can actually look at the argument from slope. So if you look at that graph that you've drawn, if you remember in the little previous part, we had a situation like this, and we had the fast car, and we had the slower car, both moving at constant velocity. And what we said is this slope here, m1, was bigger than m2. And of course, if m1 is bigger than 1, 2, what that means is that the velocity of 1 is greater than the velocity of car 2, okay, based on the steepness of the slopes. What that means is this slope is steeper. Right here, the slope is steeper than here. So what that means is since the slope is getting steeper, the car is going faster. That's such an important point. I want to write that down. So because the slope gets steeper, the car is going faster. Okay, that's the point of this graph right here. To kind of sum up this particular point here, what I would say is this. So the first point we're making here is steeper slope equals faster. Okay. Now, based on this whole idea here, what I want to actually talk about is, let me rewrite that point. So our first point is steeper slope means faster. Now, the other thing we worry about, whether we're talking about constant velocity or changing velocity, is whether something is moving backwards or forwards. So if you remember in the buggy lab, this was an object moving forwards. And that was because the slope of the line was positive. Okay, so that means V naught was positive. And remember, velocity means speed, which is the value of the slope, the number that you get when you calculate rise over run, and the direction, which means positive or negative. So a positive slope means the object is moving forward, or what we're calling forward with respect to our reference point. So we start at some initial position away from the beginning of the ruler, and we move forward this way. This does not mean this positive slope, let me just be very clear, positive slope does not mean increasing speed. As we saw from the previous example, it's not that the slope is getting more positive, it's that the slope is getting steeper. That's what decides it. So this is kind of one thing. So let me just kind of show you the other example, which is moving backwards. And this is again for constant velocity. So suppose I have a car that starts off, and we actually did this in the buggy lab. The car moves like this. So again, this is constant velocity, but notice the slope is negative. And again, this doesn't mean slowing down. Remember, slowing down means, so steeper slope means faster. Okay, so if I were to write a second point, I would say not steeper, whatever the opposite of steep is, leveling off. I'm sorry, that's such a bad word. Leveling off of slope means slowing down. So here's what I mean. This is a flat slope. So flat slope getting steeper is speeding up. I have a steep slope and it levels off. It's slowing down. That's the idea. So what we're talking about here with negative and positive slope is going forwards or backwards. So the third point I want to make is positive slope means going forwards. Negative slope means going backwards. Okay, so what we're going to do is we're actually going to put these ideas together. So here's what I mean. Suppose I have a car that's doing this. So first, I notice the slope is getting steeper. And I notice throughout the whole thing, here the slope's positive, here's the slope's positive, here the slope's positive, and here's the slope's positive. So the slope is positive and it's getting steeper the whole time. So slope is positive. That means it's moving forwards. And 2, it's getting steeper. So it's speeding up. So the way we describe this motion is we say going forward and speeding up. And this is kind of like big Roman numeral 1 for the different types of motion. Okay, and what we're going to do is we're going to look at every single one of these. Okay, and you should actually put these in your notes. So this is the first one. Now the second one is going to look like this. So we're going to have a similar situation, but now what's going to happen is we're going to do this. So here, if you notice, throughout this whole situation, here the slope is positive, here the slope's positive, here the slope's positive, and here the slope's positive. So the whole time the slope is positive. So what that means is, since the slope is always positive, we are moving forward. But notice something else. As we go, the slope levels off, meaning it starts off very positive here, but it gets flatter and flatter. So the slope gets flat, and that means we're slowing down. So the way we describe this is Roman numeral 2, and we're saying that we are going forward, slowing down. So now the situation becomes, what does going backwards look like? So let's talk about that. So we'll get rid of all this stuff here and draw a graph of something moving backwards. And it will look considerably different. So let's do this situation. We have this set up. This will be Roman numeral 3, and we're going to have a graph that looks like this. So this is moving backwards. Again, during this whole time, the slope is negative. But now look at this situation. Here we have steep slope that's negative. And here we have a less steep slope that's negative. So what this means is because the slope is leveling off, we're slowing down. And because the whole time the slope is negative, we're going backwards. So this situation is going backwards and slowing down. So that's Roman numeral 3. That's the third type of situation. Finally, let's do the very last situation that kind of all our graphs are made of, and it's going to look like this. So now we're going to have a situation where the object is moving like this. And if you notice, we start off flat, so very small slope, meaning it's not steep. And here it's very steep. And also notice that here the slope is negative, and here it's also negative slope. So this situation, remember, steeper slope means faster, so it's speeding up. And it's a negative slope, so it's going backwards.